Cisco Certified Network Associate Day 37. Welcome back everyone, I'm Imran Rafai, your trainer for this entire series. If you're following us as and when we upload these videos, then I'm really sorry because there's been a significant gap between day 36 and day 37. But if you're following us much later after I have recorded this video, forget about it, nothing happened. You just watched day 36 and now you're watching day 37. Right, so today we would be getting into two new concepts, PortFast and BPDUGuard, and of course we didn't do the bridge election from Rstp, which we are going to continue in this video, right? So without wasting much time, let's get straight into today's class. Before we go ahead, click on that subscribe button and don't forget to click on the bell icon, because that would notify you when we upload any new videos. And also feel free to click on the like buttons on the video that you're watching now. Also, check out a new video that we have uploaded last week about our new Ccna quiz engine that is there on our website. You can do a lot of things on our website. We have introduced a new thing called points, so you can get points for doing various things on our website, and you can use those points to buy things from our online store. One of the way you can earn points is by attempting a quiz. Watch our video, it explains every different ways through which you can earn points on our website. The link for that video is given on the description below, and also this is the link to attempt our quiz. So guys, enjoy. We're going to add more questions and this will be your go-to stop for testing your knowledge. Our social media contacts: on the left, my company contacts, Networking Consultant, Networking Inc. and Networking Inc. for Facebook, YouTube and Twitter. And on the right, my contacts, that's for Facebook, LinkedIn and for Twitter. For people who keep asking me what's my email address, my email address is imran.rafai@nWking.org. So what are we going to look at today? Today, like we said, we would be looking at Rstp root bridge election or selection, and then we look at two optional Rstp features called PortFast and BPDUGuard. Each spanning tree protocol, whether it is the Rsvp version, the standard Rstp version, or the Cisco implementation of PVSTP or RPVSTP, all of them have these three basic steps. Step one would be to elect a root bridge. They elect a root bridge by exchanging BPDUs, and BPDUs, there was another concept that we looked at in the last video called bridge priority. Now if you don't know what bridge priority is and other aspects about bridge priority, I would request all of you to watch the last video, that is the day 36 video again, because we have shown you exactly how the bridge priority is calculated, right? So depending on the bridge priority, one of the switch is elected as the root bridge. Like I said, bridge, switch, it's all the same because they're sticking with the old terminology. So one of them will be elected as a root bridge. Then all the other device in the network or in the switching network, it tries to find the route, the best path to the root bridge. That will be second step. So first step is elect a root bridge, second is find the best path to root bridge. And now how do you find the best path? It depends on the cost. Again, we discussed cost in the last video. So it looks at the cost to reach the root bridge and they try to find the best path. Of course, if there is again a mechanism to break a tie, so if you have two paths, both of them have the same cost, then they will next start looking at the bridge ID of the next device. We will discuss that in a moment, and then they will block every other path. That's the third step, right? So elect a root bridge, find the best path to the root and block every other path. Now let's look at these three steps in action. Now this is a regular switching network, so a network connected with 8 switches, and what I've done is, just for simplification of the explanation, I've kept all the bridge priorities same. So 32769 is the bridge priority for all the devices, and I have kept the MAC address also very simple. So all A's for switch A, all B's for switch B, switch C, switch D, switch E, switch F, switch G, and switch H, right? So it becomes easy for us to identify the switches. So when these switches come on, the first thing that they do is they start sharing BPDUs. So they would say, okay, I am the root bridge and my bridge ID is 32769CCC, or this fellow will say my bridge ID is 32769AAA, the root bridge ID is 32769AAA, right? So each of them will start thinking that they are the root bridge and they will start sending out BPDUs. So let's say switch A would send out BPDU in all these 3 ports, because these are the 3 ports it is connected to. Now when switch C receives the BPDU from switch A, it says, okay, switch A has got a better bridge ID. Now how do you say better? Like we said, better is, if you look at, first they will look at the bridge priority, right? So if the priority is less than its own priority, it would definitely consider them to be better. So in this case, both of them are same, so obviously there is a tie. Then they look at the MAC address. AAA is better than CCC. Better is always lesser is better in switching STP world. So AAA is lesser than CCC, so switch A would become the root. I mean, in this thing they would consider him to be the root. So now switch C would start sending out BPDUs, updating, saying the root bridge is 32769AAA and my bridge ID is 32769CCC. Now when this device EEE receives that BPDU saying that the root bridge is 32769AAA, it would also say, fine, I think AAA is much better than EEE, so yes, root bridge is AAA, and it would start sending out BPDU out. And similarly, after a while, they would all accept that switch A is the root bridge, right? So now switch A becomes a root bridge and everybody accepts this. Now the next step is for all these devices to find the shortest path to the root bridge. So how do they do that? Let's assume all these devices are connected by, let's assume, fast Ethernet, and let's assume the cost is 19 for each of these paths, right? Now when the root bridge sends out BPDU, it says I'm the root bridge and the cost to reach me is 0, right? So it sends out cost of 0, it sends out cost of 0, it sends out cost of 0, right? Obviously, because it is the root bridge, and obviously it doesn't have any cost to reach itself, right? When switch C receives that, it says, okay, you're telling me that you can reach root with a cost of 0, right? That comes on this link, but it says for me to send out on this port, I have a cost of 19, right? So it says for me this port, the root cost is 0, which he sent, plus 19, which is 19. That's fine. The same way, this device also will tell that this is the root cost on this port is 19, and this has a root cost of 19. Now when switch C sends that BPDU to switch E, it tells, you know what, I have a root cost of 19, so it sends out BPDU with cost 19. Now when switch E receives that, it tells, okay, you have a 19 plus I have a 19 to use this link, so root cost for this port is 38, right? Similarly, this device also will send a 19 to this, so this will have a root cost of 38. You see where I'm going with this? Now this device will have to choose between these two ports. It would say, yes, my root cost is 19, which is better, so it will send out 19 to this guy as well. Now this guy, switch F, takes that information and says, you're telling you have a switch cost of 19 on this port, I have to add a 19 to reach to you. That means the port cost on this port is 38. Similarly, this guy also will send out a 19, so the root cost would be 38 on this port. So Now you see how these costs are getting calculated. So eventually all of them will have a root cost on all the ports to reach the root, right? So each of them will say, okay, now for instance, this device would say I have a root cost of 38 here, but I have a root cost of 19 here, so this is my root port. Now this is 38 and 19, again this also will be 30, no, this will be 38 plus 19, that will be what, 60, 50, 57? Yeah, 57, right? I'm sorry if my math is all wrong. 19 into 3 is 57, I believe. Yeah, so 57. So between these three, this has to be the root port. Between now these two, this will not take him to the root. So between these two, he has a root. I mean, it's a tie. So between these two, he has to now, because it's a tie, he has to decide between the next MAC address, right? So the MAC address of uplink switch is BBB. This is better bridge ID than EEE bridge ID, so he will make this as the root port, right? And in this case, obviously there's only one link that's connected, so I mean he can do by this way, but this is a shorter cost as we discussed, and this is going to be the root bridge, right? Or the root port, I'm sorry. So after the evaluation, like we discussed, they would choose the root port. So in this case, this is a root port, this is a root port, and this is a root port, and all the other devices which is indirectly connected to the directed link. Now just because it's directly connected, that doesn't make it root port. Let's say if this was running on Ethernet and these were all gigabit Ethernet, obviously depending on the cost, if you want to look at cost, go to the last video. I have explained the cost. So depending on the cost to reach the root port, that port will become the root port. In our case, since we are keeping it very simple, we are assuming all of them are fast Ethernet and they all have equal costs. Next, the other devices also will calculate its root port, so all of them will have a root port chosen. Next, every port on your root bridge will be a designated port. So we have chosen the root port now. Now every port on this root bridge has to be a designated port, because designate port, if this is the root port and if at all you block, if the root if the root bridge blocks this port, obviously this switch cannot access the root bridge, right? So as a general rule, all the ports of the root bridge would be a designated port. A designated port is a forwarding, it will be in a forwarding state. So the root port has to communicate to root bridge and it can't be in a blocking state. It has to be in a forwarding state, and hence it will be in a designated state. And similarly, every link which has a root port, the other end has to be a designated port. So it will be a designated port here, 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 and here. So that's how you chose. So you chose the root port and you chose the designated port, which is the other end of the root port. That's done. Now we have three paths. Now this path, and this path, which does not have a role defined yet. So now between these three paths that is not chosen, we have to make one side of that, and these are the links that actually creates loops, right? If you see, these are the links that actually create loops. So this has to be logically disconnected. So one side will become a blocking port, and it becomes a blocking port, and then it disconnects that link logically, and the other side obviously has to be a designated port. Now who decides, like for instance in between these, who becomes the blocking port? Which of these devices, whether switch E or switch C, who will block the port? Now how do we do that selection? So again we go back to the thing as cost. So first, between root C and switch C and switch E, who's got the lowest cost to reach the root bridge? Now if you know what we did, both of them have the same cost. So like I said, the first is cost, so both of them have the same cost, so that's a tie. Next tiebreaker is the bridge ID, BID. Now 32769 CCC, 32769 EEE, between them CCC is a lesser as in better bridge ID, which is a lesser number. So this will become a designated port, and this will become a blocking port, right? Now, in case, like for instance, if both of them are let's say if they were one device, like for instance it was one device and connected to, we're talking about two links from the same device, both of them will have the same cost, and then you will have both of them will be part of I mean the bridge ID would also be the same. In that case, there'll be a third tiebreaker, which would be the port numbers, right? So port numbers, you look at the port numbers, it is connected to port number, which is the port number. The lower port number becomes the designated port, the higher port number becomes the blocking port, right? So that's how you do. So first tiebreaker is cost, then bridge ID, then port number. So in these devices, as we discussed earlier, this becomes the blocking port. Between these two, again it look at the cost. So the cost, this cost is 38, this cost is 19. So obviously between these two, this has to become a blocking port, right? That's how this was decided. And in this case, like we said, it decided on the basis of the bridge IDs. Now this link, the cost to reach, because both of them are connected to the same switch, this switch has a cost port root cost of 38. So this has root cost of 38 plus 19, that's 57. This also has root port cost of 57. So both of them have the same cost. Obviously the next thing that they do is look between the bridge ID. So bridge ID DDD is better than bridge ID GGG, and that's why it is chosen as the blocking port. Now when it's a blocking port, it's physically not disconnected, it is just logically disconnected. That means it's not going to look at any traffic or loops on that link. That's what it does. It would still receive BPDU. So let's say if this sends the BPDU, it would still receive those BPDUs, but it's not going to process any traffic, right? That's what happens when the port is in blocking. Obviously this whichever device is chosen to block, that will not send out BPDUs. It will not send BPDUs out on those ports, but it would receive BPDUs and it would process and calculate, but it will not send out traffic or BPDUs on that port. This is how a root bridge election and the whole STP process is taken care of. So once you do these can be simplified because these are blocking ports. It's as good as that port not being there. So if you look at it, all these devices now only have a non-looping one path to the root bridge. This is what a spanning tree protocol is all about. It's very, very simple. Takes a looping bridge, a looping topology, it breaks that loop and it becomes like a bridge. So the name spanning tree comes where you have a root of the tree and you have different branches of the tree, right? So this is what happens now. So if you look at this as the root, you have different branches of the tree going in different ways. This is the simplest way I could explain spanning tree protocol for you. If you guys like it, hit that like button, don't forget. Next, we look at the need for rapid spanning tree. We I think had a very brief discussion of rapid spanning tree, and then of course we looked at some of the topologies, and I told you what the difference between a rapid spanning tree is. But why do we need rapid spanning tree? Now if you remember from our last discussion, we said that 802.1d, which is the standard spanning tree protocol, had a transition delay of 50 seconds. That means if a port is in a blocking, it waits till it misses 10 hellos, right? 10 into 2 seconds. 2 seconds is the default hello. Of course you can change that, you can make it into you can tune this hello timer to different times. So basically it's 10 into 2. By default it is 20 seconds. Then you have a listening, then a learning before it goes to a forwarding state, right? So from blocking to forwarding state, it takes about 20 seconds, then 15 seconds of listening, 15 of learning. So that's about 30 plus 20 is total 50 seconds. So we discussed this. Some of the newer devices can boot in like 5 to 10 seconds. Now think you're coming into your office and your PC is connected to one of the ports because your device is shut down. Your computer, that port would be in a blocking state because there's no point of that being in any other state, or a discarding state or a disabled state. Now for it to start going into a forwarding state, it is going to go through all these processes. So before the switch port becomes in forwarding state, your computer would be up and running. And if your computer has to log into your domain, Active Directory or any of those logins, you can't do that because your computer still does not have access to the network, because the port to which your computer is connected to is still not in forwarding state. That's a problem. You could then, you would think you're not connected, you will try logging in, it doesn't work, you call the customer service. A lot of all those issues come in because your switch does STP and it is very, very slow to transition to a forwarding state, right? So that is definitely a problem. We have a temporary solution, or a solution that is easier to implement, that is called as PortFast. Now all the edge devices where you connect. Now what is an edge device? In your network, like we saw, we have multiple switches, right? But the port that is connected to a non-BPDU device, like a computer or end devices, those are called edge ports, right? Edge ports, not edge devices, edge ports. So these edge ports can, because obviously these edge ports don't receive, or technically it shouldn't receive BPDUs, we can make those ports into something called as PortFast. That's a Cisco technology called PortFast. All you have to do is go into that interface and say spanning tree PortFast. That's a very simple command. Go give that command and that device becomes instantaneous. So that device does not, it basically disables spanning tree on that port. So when you plug a device, immediately that is in forwarding state and it does not have to go through all these transition states. That's good. But the problem is, if let's say you have done this and then later, maybe after 1 year or 2 years, you don't realize that this is already in PortFast mode, you connect another switch onto this, right? When you connect the switch onto this, it could potentially, because there's no spanning tree working on that port, it could potentially create a temporary loop, right? It creates a temporary loop, and then you have these loops, and then eventually it takes some time for a spanning tree to realize there's a loop, and then it sorts out. But temporarily it will create a loop. To prevent that, there is another technology called Bpdu Guard. Bpdu Guard, if you enable, again it's on an interface level that you enable that spanning tree Bpdu Guard enable, you give this command onto a port that is in PortFast. What it does is it would guard to make sure that it does not receive any BPDU. So the minute you do this connection of a switch to another BPDU PortFast port, if it receives a BPDU, this command, the Bpdu Guard feature, will immediately put this port into an error disabled state, right? Error disabled state, and it will stay there. So then once it's in error disabled state, that port will not work. Technically it's in a shutdown mode, right? It is in error disabled state until an administrator goes there and removes that error disabled state. It will not work again. So if you enable this PortFast, it protects that port. Of course, it makes PortFast makes the port go faster. It disables spanning tree, and if you enable the Bpdu Guard, it protects itself from receiving a BPDU message. So these are the true features. Now again, these were, like I said, these were temporary solutions, or at least to make it temporary solutions in the sense that it was done to improve the transition time. Then of course IEEE 802.w, the Rsvp standard, was implemented. Now the difference between the two, STP and Rstp, is of course IEEE numbers. IEEE 802.1d is STP, 802.1w is Rstp. So this is something that you can learn. It's very easy. The next thing, like we discussed, the conversion times of 50 seconds on STP. So that's 20 into hello time, or 10 into hello times is 20 seconds, 15 seconds of listening and 15 seconds of learning. Conversion times of Rstp is 6 times the hello timer, or rather 3 times the hello timers, that is 6 seconds and 15 seconds of learning. Now again, ideally, if all your devices are running Rstp, these don't really come into play. It's almost always instantaneous, right? It's in 0. But if you have an Rstp switch and an STP switch, they don't, because an Rstp switch, Rsvp BPDU, can understand STP BPDU, but an STP BPDU, or rather STP switch, will not understand an Rsvp. So let's say this is an Rsvp and this is STP. If the BPD coming from here to here, that's fine, it will understand because Rsvp is backward compatible, it can do it. But the BPD going from here to here, your STP's old 802.1d will not understand the format of Rsvp BPDUs. So this will most probably get dropped, or it will not understand what happens. If you ask me, BPDU between Rsvp BPDU and STP BPDU, they're very, very similar. There are very few features that is like you have some flags that is implemented, like in STP BPDU, the flags, they only use 2 of the 8 bits, but Rsvp BPDU, it uses the entire 8-bit to different states. Now I'm not too sure if you need to go that in depth in Rsvp or STP at a Ccna level, so I will not go in. Let's leave it at that, because going in too much, I think it's like a CCNP level topic, so you don't need to know about it. Whatever we're going to teach you, that should be more than enough for your CCNA level. So like I said, it's most of the time they work on something called as a proposal and agreement, Rstp. So Rstp devices send, if both of them are Rstp, let's say for instance between 2 switches, now it says D but they are actually switches, lazy me. Okay, so both of them are working on Rstp. Typically how it works is the device, instead of saying, when it's sending a BPDU, it sends a BPDU to the new device and it blocks its port. So it sends the BPDU and it blocks its port. The receiving device looks at that BPDU and looks at its own database. It says, does the new BPDU give you a better route cost or route path to go to the root switch? If it is yes, it sends a proposal asking him to open this port, right? And it will block its other ports, right? And it will send a proposal and there's an agreement, right? And then once you do that proposal agreement, it's immediately open and this link is up. In STP state, like we looked at, if at all a transition has to happen from a blocking to a forwarding state, it has to go through 50 seconds of transition time. So that's why it says 0 seconds or almost instantaneous if it is doing Rsvp and all the switches, right? Next we look at states. STP had 3 states. It had a blocking state, then a listening, learning and forwarding. So these are the 4 states in STP, that's 802.1d. Rstp has only 3 states. So basically these 2 states go into a discarding state. Listening stays listening, mostly used when you are interoperating between STP and Rstp. And then you have the forwarding state, which is a forwarding state, right? So this is the difference between the states from Rstp and STP. Then we have port roles. Now as we looked at STP has root port, designated port and blocking port, where Rstp has similar ports. Root port and designated ports are the same, it's exactly the same, Blocking port are split into two now. So you have a blocking port which is alternative port, and there's a blocking port called a backup port. Now what's the difference, you would ask? In STP, let's say there is one device here, right, and there's another, let's say, hub, right, and let's say there's another switch, right? This is switch A and this is switch B, right? So if you look at this, because this is a hub, this is still considered as one path. So let me take another color. So this is still considered as one path, right? Now let's assume this is the root port RP, and obviously now between these two it has to, and let's say this has a root port RP. Now this has a link that's connected between A and B. Now according to what we looked at STP, now this has to block one of these ports, and let's assume this has a better bridge ID because it's AAA. This is blocking port and this is the designated port. Now in STP, the ports roles for this port in switch B would be like one blanket statement. It's a blocking port. There's no differentiation between a backup port or an alternate port. It's a blocking port. But if we are doing Rstp, this would be not called a blocking port because there's no blocking port. It has to choose between alternative port or a backup port. This will be an alternate port. Alternative port is where the BPDU received on that port is from a different bridge, right? That's why it's called alternative port. Now let's assume if there was another hub here, right, and we have two links to the hub. Again, because it's a hub, this whole thing is another segment, and it has to decide to make one of them into a blocking port, right? If it is STP, again, like I said, it looks at the cost is the same. It looks at the bridge ID. Again, bridge ID is the same because both of them are connecting from bridge B. Next, it looks at the port numbers, and whichever is the lower port becomes the designated port, and whichever is the higher one, that becomes the blocking port. So in this case, let's assume this becomes the blocking port. Now, is this port alternative port? No, it's not an alternative port because the BPDU received on this is sent by switch B itself, right? So it looks at the BPDU received on that port and it says it's a BPDU received from myself. So that means it is connected to the same segment. It's a shared segment. So it will say this becomes a backup port because it's technically my own BPDU that is coming back to me. So Rstp can differentiate between alternative port, that is a port that is connected to a different switch, and a port that's connected to itself. In STP, if there was a situation like this, it wouldn't be able to differentiate between the alternative port and a backup port because for STP, both of them are going to be a blocking port. So I hope we're clear with the difference between alternative port and backup port. Now, let's assume an STP is in converge state. If at all I take a wire and connect to the root port, what would happen? Root bridge would say, fine, I have a new port. I'm going to send a BPDU out here. It will naturally send a BPDU. This device, now when it receives this BPDU, it receives a BPDU with a cost of 0. And it says, all right, you're saying you are a cost of 0. I have a cost of 19 on this port because 0 plus 19 is 19. On this, because this was 38, 57, and 60, no, what was it? 20 into 4 is 80, 80 minus 4 is 76, right? So this has a port of 76. This is my way of calculating because all of them are 19. I make it 20 because it's easier. 20, 20, 20, and 20. That's 80, and it's not 20, it was 19, so I minus 1 on each. So 80 minus 4 is 76, right? So don't worry, guys. However way you're comfortable calculating, please calculate. But this has a port of 76. and this has a port cost of 19. So this becomes this has to now go from a disabled state to a transition state. That means it would take about 50 seconds, and if there are more devices connected here, all of them are lost connection to the root bridge and because it's lost connection to the root bridge, it is literally lost connection to the whole network for 50 seconds. Similarly, this will also send out BPDU saying it is a cost of 19. He takes that and he says this has got a cost of 57. You're telling 19 plus 19, this has a root cost of 38. So I'm going to put this off and I'm going to transition this. So transitioning time of 50 seconds, 50 seconds. So literally we have broken this whole network. This is STP for you. What happens if the same thing is done to an Rsvp switch? So like, let's say the whole network is converged now, and I connect a new link from the root bridge to this switch H. Immediately, what the switch root bridge would do, it would send out a BPDU and it will block this port. So you have a root bridge, BPDU sent out on this, it sends to H a BPDU and it blocks its own port. When switch H receives that, it takes that BPDU and realizes that it has got a better path to reach bridge A. So immediately it blocks this port. It sends a proposal to bridge A telling him that you are a better path for me, so please open this port. And bridge A sends fine, we can do that, and it opens this port. So this port is open now and this becomes the root port. Transition is immediate because they did it with something called as a proposal and agreement of Rstp, right? Similarly, this device now sends a BPDU to this device, switch G. So any devices that's connected here does not go through any disconnection because switch H has already transitioned itself to root port, and this is become an alternative port now, AP, right? Because it knows that it receives BPDU because earlier it used to receive, so there is a path to route through this. So this is definitely an alternative port and this is a root port. Similarly, when this device receives that same BPDU, it looks at its own BPDU and it realizes this is a better path, so it sends a proposal agreement. This becomes root port, this is disconnected, BPDU sent out here, BPDU sent out here, and again when this device receives that, this was 1938 and he would receive it at 57. He's already at this is 38, so if he receives, let's say, a 38 plus 19 is a 57. So this switch F looks at that and says, you know what, I already have a better path, so I'm not going to send you. So this port stays blocked, this everything else remains the same. Now on this port, again it's the same thing. It sends it out, it looks at that path cost and it realizes it's the same for him and he just leaves it there. So you see the difference. This transition from root port to root port was blocked, but since switch F did not request for reopening that by using its proposal and agreement contract, it did not open this port and this port becomes a blocking port now, right? So Rstp is very, very fast and you will not have any problem, and the ones that you have in STP. Right, so now let's look at the commands. So how do we enable commands? So if you want to like now we are looking at Cisco, we are not looking at STP or Rstp. Instead we'll look at PVAST and RPVST, right? So you go to the global config mode and say spanning tree mode, and you decide between PVST or RPVST. That's how you choose between PVST or RPVST, and RPVST is the rapid version of it. Next we look at how to change the priority, right? So since we are doing PVST again, we need to now give per VLAN. So we go to spanning tree, then you give VLAN and give a VLAN number. If you're doing VLAN 1, you say VLAN number 1 and you say priority, and you need to give a priority value. So if you remember, priority values, like I said, would be a multiple of 4096. We looked at it, why it is a multiple of 4096. If you go back to last video, so it is going to be a multiple of 4096, and by default the priority is 32768, right? So by default it's 30768, and like we discussed in our last video, it is always going to be 32768 plus the VLAN number. In this case it is 1, so if you're doing VLAN 1, the default priority is going to be 32768 plus 1, it's 32769. So that's how you change the priority. Now, ideal question is, why do you need to change the priority? We know bridge ID comprises of priority and MAC address, right? MAC is something that we can't change. It's fixed, it's permanent. This is what we can change if you want to tune. Let's say we have a network, right? We have a large network. This is not large, but assume you have a large network. And let's say there's a loop. If nothing is changed, by default PVST is on a Cisco switch. So if Cisco switch, you're connecting them in a loop, automatically, because since all of them have the same priority, the device with the oldest MAC address will become the root bridge. Now, the oldest device in your network could be a very old switch. It could be a switch that's about 10 or 15 years old, and it doesn't even have the power and capacity of a modern switch. So maybe this is your best switch. It's a very expensive switch that you bought, but the oldest MAC address in the network is a switch that is like $200 worth per switch. It's a cheap switch, or a $100 switch. Ideally, you wouldn't want that switch to be the root bridge. If it's a root bridge, now what will happen is all traffic will have to go through that before it exits the network, and that would be it would be a big design failure if that's not your central switch. So you would want to make this as your root bridge every time. So you would go there and manually put a priority that is very low. You put a priority of 0. If you want, you could put a priority of 0. So it'll be 0 plus VLAN number 1. So you will have a priority of 1. And all the time, if none of them have the same priority, all of them will, all the time, this will be your root bridge, right? That is for you to manually put the priority, like if you want to do priority manually. But another way of doing, let's say you have, like, these are your two best switches, like all two best switches, and you want this to be root bridge. If this, for some reason, if this bridge is not available, then use this switch as your priority, right, as your root bridge. In that case, you can go to this switch and say spanning tree VLAN 1 root, and you can give the keyword primary, and you can come to this device and say spanning tree VLAN 1 root secondary. What it does is, in this switch, now let's assume all of them have the same priority, 32768. When you give the word primary, when you give this command primary, it does is it minuses 32768 minus 4096, it minus twice 4096. So whatever that number, that is the priority for the primary device. For the secondary device, it minuses 32768 only once, 4096. That's the whatever that priority. So basically, you don't have to manually put in a number there. It would automatically do that for you. So it's a very simple command, say primary and secondary. It will automatically make sure this is going to be the first device that is going to be root. If that's not available, then this device becomes the root, right? So that is how you make sure you are in control of your network, and you don't let spanning tree automatically decide who should become the root bridge, right? So that's that. And if you want to look at the spanning tree, you can use this command called show spanning tree summary, and that should show you the spanning tree. Let us now look at all the concepts that we learned in today's video using packet tracer. I have 4 switches, 2960 switches. It doesn't matter, all the switches on packet tracer can do STP. So take 4 switches, let's create a loop, or let's connect these switches across and make a loop. So from switch 0 to switch 1 to switch 3, switch 3 to switch 2, and switch 2 to switch 0, and you see that all of them are in amber state. That means their STP is running in the background, and by default Cisco devices run PVST plus. So PVST is like STP 802.1D. that means each of those ports would take approximately about 50 seconds to converge, right? So it's a lot of time. If you go to we can go here, actually check. So yeah, so it says STP, so switch 1 to switch 0, or rather at switch 0 it says inbound STP. This is the STP frame type, so you have protocol version. So difference between BPDU of STP and Rsvp is this. So when it is version 0, so if it only BPDU frames are shown to you in the test, by looking at version 0 you should know that this is STP. If it is Rsvp, it would be version 2, right? So at the moment, what is it saying? It's saying the root ID is 32769 ending with 2658, and the bridge ID is 2658. So this is at switch 0. That means this particular device is the bridge ID. It's telling that it is the root, so most probably switch 0 would have become the root. That's why it is saying that the root ID is also the same as itself, right? Bridge ID. So that is if you want to look at a packet level. Now I think they have done what they had to do using STP. A root bridge election is done, and STP has put, I believe this port has gone into a blocking state. The switch 2's port, I think this is the F0/2 port of switch 2, has gone into a blocking state. So let's go in to the switch, right? There are two commands. One, we can do show spanning tree, and if you hit enter, it would tell you a few information. So it says it is this. Now this is PVST, right? PVST plus. PVST plus, it is working on this particular information that is shown here is related to VLAN 01. If you had multiple VLANs running PVST, they would have another set of information below here which says VLAN 02, 03, whatever, and then you'll have the same set of information. So it says spanning tree enable with protocol IEEE, right? So when it says IEEE, that's your clue that this is PVST. Cisco doesn't do 802.1D. So even though it says IEEE, what it means is it's running PVST plus. PVST plus, like you know, it's compatible with IEEE, so it is running 802.1D technically, but in per VLAN. So every VLAN runs an instance of 802.1D. So this is that, and it says root ID. So this is information about the root. So it says root has a priority of 32769. If you remember 32769 we discussed in our last video. The MAC address is this one. This is the bridge ID of this particular device. So switch 0's bridge ID is 32769006559. Okay, so I was wrong. This is not the the root. So switch 0 did not become the root in this case. The root is a device that is ending with 2658, right? I think earlier when we looked at the STP frame, I think it was an inbound PDU that we were looking at. It was not the outbound. So yeah, it must have got an inbound PDU from one of the other devices connected. So we'll look into it. So at the moment we know that this particular device is not root. Another way we'd know that it is not the root is because a root switch will not have a root port. So in this case, one of the port is root port and the other port is a designated port, right? But both of them are in forwarding state, so that's fine, but one of the port is in root. Another thing we need to know is this type. It says P2P, that is point to point. So the FA01 is connected to another switch, that's why it's point to point. FA02 is also connected to another switch, that is why it is point to point. Had it been connected to a hub, it would be another type called a shared. We'll look at that in a moment, but for now these are the two interfaces, and we can look at their state and their role. Another show command is show spanning tree summary. So if you do show spanning tree summary, it would tell that this particular switch is in PVST mode. So here it tells you the protocol that is running, and here it would tell you the mode. So this is PVST mode. So if you put this command show spanning tree summary, it would tell you the mode. So PVST mode, and then it says extend ID is enabled, then all of these are disabled. So PortFast is disabled, PortFast BPDU Guard is disabled, Bpdu filter is disabled, and all these things are disabled. It tells for VLAN 1, 0 blocking, 0 listening, 2 are in forwarding, and 2 of those are working STP. So both the ports are working, STP is running on that, and both of them are in forwarding state, right? So that's that. Let's look at this switch 2. Or before that, let's look at this switch. So let's do the same command here, show spanning tree, and in this case the same thing, VLAN 01, priority route is 322658. It's the same as the previous device, because in an STP network all the device will have this field same. Once the network has converged, one STP has converged and everybody has the same database, they will all believe this information, because that's what route election is. So after route election, everybody has accepted that 2658, this particular device, is the root bridge, and this is the root bridge. So technically we have found out which is the root bridge. In this case, this device is the root bridge, and you would have a message here. Yeah, this says this bridge is root. So this is your another clue which would tell you whether this is the root bridge, right? Another way is, you might in your test you might just have this output shown, and it'll ask you whether it is a root bridge. One way you could know it's a root bridge is that it does not have a root port. It has all its port as designated port, right? So if it's all ports are in designated port, and if all ports are in forwarding state, it definitely has to be a root bridge, right? So let's look at another thing. Let's look at this, because in this one, switch 3 also will have the same information. Let's look at switch 2, because switch 2 will have one of its port in blocking. So show spanning, right, and we would see that the same information. Like I said, the root has to be the same. Root will not change to 658. This is the root, because that's after election they've decided that this is the root. This bridge ID is 5AE1. Again, see, the priority is the same, 32769, 32768 plus the VLAN number, VLAN 1, that is why you get 32769. Here you would see that one of the port is an alternative port. Now don't get confused, 802.1d called it a blocking port, but PVST always called whatever blocking port it is called as alternative port, right? So it's an alternate port in PVST, which actually is the same as the blocking port. In Rsvp there was another alternative port and backup port. So PVST cannot distinguish alternative and backup. It is still going to say alternative even if it's a backup port. But when we move to our rapid spanning rapid PVST, RPVST, then yes, it would do that alternative for alternative and backup for backup. But at the moment, if you're running PVST, whenever you see alternate, it actually means the backup, the blocking port in 802.1d, right? So 802.1d, you see one of the port, FA0/2, is an alternative port, but it is in a blocking state, right? So this is a blocking port now, and FA01 is a root. So basically this is the root, and this is how it is accessing the root, and switch 0 is directly accessing the root. Between switch 0 and switch 2, one of them had to be a blocking port, and after they did the STP, they decided that switch 2 would block the port, right? So that's how switch 2 has blocked the port. So you have alternative port, blocking port on FA0/2, and like we discussed, P2P, because we don't have any interface. And like we saw, STP takes a lot of time to converge. Now this is a converged network. We take this wire from here and we connect to the root. So we give a new root. So if you see here, switch 2, now all the ports in the switch 2, let's quickly do show spanning tree summary. We'll see that 2 of those ports, one is in blocking, 2 of them are in listening now, and this has always been blocking. That's fine. Now the earlier root port has also gone into listening. The new port also has gone into listening. Then they will go into learning. Now they are in learning, both of them. They're going to learn and they're going to see what is the thing. Once they finish learning, then they would go to forwarding. So now you see this particular port, right? This particular port has gone into blocking now, and this has become the root port. So we could look at that here. We could go show spanning tree, and you would see FA0/1, which was the earlier root port, has gone into alternative or blocking port. FA0/3, which is our new direct connection to, that has become the root port, and FA0/2 has become a designated port, right? So it took a lot of time. Now, if the same thing happened using Rsvp, now let's do this. Let's change all the switches to Rsvp. So I'm going to do this. I'm going to disconnect this connection again. So again, they would run because the root port is gone. So they will have to go through all their STP process. And eventually, so let's look at this. So now you'll see one of the port is in listening mode. So it's going to go to listening. It will then finally discuss. If you see here now, both of them have gone down. So both of them would be, one is gone to blocking, the other is going to learning. So now both, you've seen that it took a while for them to, any change in topology takes a time. It takes a while for it to recalculate. Now let's change all the switches to run Rsvp. So I'm going to go to switch 2, start with switch 2. How do we change to Rsvp? Spanning tree mode rapid PVST, right? So there are only two options here. If you see PVST or rapid PVST. So I'm going to say rapid PVST. Right now the switch is running rapid PVST. How do we check that? We can go here, spanning tree, sorry, show spanning tree. If you do show spanning tree, it would say show spanning tree protocol is Rsvp, right? Nothing else changed, everything else is exactly the same. Then we do this, we say show spanning tree summary. Now it would say switches in rapid PVST mode. Everything else is exactly the same. I'm going to do the same thing with all the other devices. Right, so I have just made all of them run rapid PVST. I have not done any more changes. That's the only change I've done. Now let's do the same thing. This is exactly how it was with STP earlier, or PVSTP, PVST plus earlier. We took a wire and we created a connection. So I'm going to do the exact same thing that I did earlier, and let's look how quickly this converges. Right, I did this change, and you will see that switch to show spanning tree summary. You would see that two of them gone to blocking, one is in forward, and all three are running RPVSTs. That's how quickly they made that decision, right? So that was fast compared to PVST, which took a lot of time. RPVST is rapid. It quickly makes a decision, and they have changed. So that's how fast it is. Some of the other things that we need to look at is spanning tree. We looked at spanning tree mode. Then we could look at spanning tree PortFast. So if you do PortFast, and if you say default, this is to enable spanning tree PortFast and all the ports of the switch by default. This is if that's an edge switch, right? And all the ports, or majority of the ports, are going to be edge ports, right? It's directly connected to a host. Then yes, we do this, and then we'll go to those specific ports which are not edge ports, and then we change it back to run spanning tree. So this is how you do that if you want to do global level. Then what are the then we have spanning tree VLAN, right? And then we say VLAN number, VLAN 1. We can say priority. So if you want to change the VLAN priority, this is where we come, spanning tree VLAN number, then you come to priority, and then we can give any priority from 0 to 61440, and like I said, it is going to be in increments of 4096. So you could give it 0, or you could give 4096, right? This is how you manually change the priority. Then we could look at root. So if you want to remember, I told there are two commands like primary or secondary, so you could do that here, spanning tree VLAN 1, and then for VLAN 1 the primary is this. So if you say primary, that this particular device switch to would become the primary root for this device, and if you say secondary, then it would be the secondary device, right? So that's how you do the collection. Now since they all in RPVST, if I say primary here and I hit enter, immediately this switch 2 will start becoming root, and everybody will negotiate. So already the negotiation has happened. This is very fast. Now all the switches already converged, right? All of them have converged. They have made the decision. Now if you go back here, let's look at show spanning tree, and we'll see that this switch has a priority of 24577, right? And this is the MAC address. So you see this is the root now. So they've done, and this is the root, and they have already converged. That's how quickly it does what it has to do. Then let's go to FA0/1, or let's first go to this particular switch and change that mode. Let's say no spanning tree VLAN 1 root priority. So I'm gonna take this back. So I think now do show spanning tree 32769. It's gone back to the old priority. I think they will do. I think they've already done the calculation, and this switch has gone back to becoming the root. Show spanning tree. Right, so this is the root again. Let's look at how to do PortFast. So PortFast is interface F0/1, any interface. We say spanning tree. Then here we can enable PortFast. So you say spanning tree PortFast. We can say you hit enter, it would enable PortFast. If you want to disable, you say spanning tree PortFast and disable, right? That's how you enable spanning tree PortFast. And again, BPDU Guard is spanning tree BPDU Guard, and hit the command enable to enable it, or disable to disable it. We discussed what is PortFast and what is BPDU Guard, and these are the only two concepts that we need to really discuss. Part of Ccna, so I'm not going to discuss any of the other ones there. One more thing I want to quickly tell. I think in our previous explanation in today's video, I forgot to explain one more thing. We should know it by now. PVST is per VLAN STP. So basically, each of those interfaces will have a separate instance of 802.1d. Now, when that happens, what is critical is for VLAN 1, this could be the blocked path, but from VLAN 2, this, depending on how we configure VLAN 2 priority, this could be the root bridge, and this interface, which is actually not being used in VLAN 1 STP, could be actually used in VLAN 2 here. So that way what happens, there is a load balancing happening in a way that in some of the STPs running on VLAN 1, a certain path is not being used, but in the others that path is being used. So that's something that we need to be very, very critical. So you need to understand that load balancing is happening because of the per VLAN instances of STP. One last thing that I want to show is what happens if we have a shared interface. So let's say we'll put a hub. I'm going to put a hub here, and I'm going to connect two wires. So wire here and a wire here, and let's see what happens to this. Show spanning tree, right? You would see that FA05, like between this interface, FA05 is the backup port, this particular interface FA05, and FA04 is designated, right? But you can see that both of them are shared here, type, so that means it is looping through a shared interface. So this whole interface path is a shared path, right? Because we are in Rsvp now, it can differentiate between backup port and alternative port, right? Now if we change this same switch, configure terminal spanning tree mode PVST, right? This interface FA05, now it's going back to its STP discussion. So once it finishes discussing what it has to discuss, we would see that this particular port FA05, it is they've gone back to calling it alternative port because it does not differentiate between a backup port and an alternative port, right? So that's the difference between a backup port and an alternative port. This is a very long video. I hope you guys have understood the concepts here. If not, watch this video again, and that will conclude our spanning tree. I think we have covered everything that is required for your CCNA in spanning tree. Stay tuned, we'll be back very soon, and we'll have much important and very interesting topics like OSPF and EIGRP is coming very soon. So people have asked me, when is EIGRP coming, when is OSPF coming? Very soon. Stay tuned guys, we will be back. Thank you so much. Bye bye.